The story of variable stars begins long before modern telescopes, rooted in the earliest observations of the night sky. Ancient astronomers in Egypt, Greece, and China noted that some stars seemed to brighten and fade over time, but they had no way to explain these changes. To them, the heavens were perfect and unchanging, so any variation in a star's light was seen as a strange anomaly, not a key to scientific truth. It was not until the late 16th century that European astronomers began to study these stars with systematic curiosity. The first documented discovery of a variable star came in 1596, when a German astronomer named David Fabricius noticed that the star Omicron Ceti, later named Lyrae, would vanish from sight for months at a time before reappearing and brightening again. This was a revolutionary observation. It proved that stars were not eternal and unchanging, but dynamic objects that evolved and shifted over time. Lyrae, a red giant star, became the first recognized long-period variable star, with a brightness cycle that stretches over 330 days, a slow, majestic pulse that marks the final stages of its stellar life. This single discovery cracked open the door to a new field of astronomy, one focused on the stars that change. As telescopes improved and astronomers began to catalog the sky, more variable stars were found, and scientists started to classify them based on how and why their brightness changed. Today, we know that variable stars fall into two main categories: intrinsic variables, whose brightness changes because of physical processes inside the star itself, and extrinsic variables, whose light shifts because of external forces, like being blocked by another object in space. This distinction is critical to understanding their behavior, and each category holds stars that have changed the course of astronomical history. Intrinsic variable stars are the true heart of this story, as their light variations come from within. The most famous and scientifically vital type of intrinsic variable is the Cepheid variable, named after Delta Cepheid, the first star of its kind, discovered in 1784 by the astronomer John Goodricke. Cepheid variables are massive hot stars that expand and contract in a regular pattern like a cosmic heartbeat. As they expand, their surface area grows and they brighten. As they contract, they shrink and dim. What makes Cepheids so extraordinary is a relationship discovered in 1912 by Henrietta Swan Leavitt, a brilliant astronomer working at the Harvard College Observatory. Leavitt was studying Cepheid variables in the Small Magellanic Cloud, a satellite galaxy of the Milky Way, and she noticed a direct link between a Cepheid period, the time it takes to complete one brightness cycle, and its true brightness or luminosity. The longer the period, the brighter the star. This was the single most important discovery in modern cosmology, the period-luminosity relationship. For the first time, astronomers had a standard candle, a celestial object with a known luminosity that could be used to measure distances to faraway galaxies. Before Cepheids, we had no way to know how far other galaxies were from the Milky Way. We could see them, but we could not place them in the vastness of space. Cepheid variables turned the universe from a mysterious, unmeasurable expanse into a map we could begin to read. Another key type of intrinsic variable star is the RR Lyrae star, named after the star RR Lyrae in the constellation Lyrae. These stars are smaller and older than Cepheids, typically found in globular clusters, dense groups of ancient stars that orbit the Milky Way. RR Lyrae stars have short, consistent periods, usually less than a day, making them perfect for measuring distances within our own galaxy and to nearby globular clusters. They are like the cosmic yardsticks of the Milky Way, helping astronomers map the structure and size of our home galaxy with incredible precision. Together, Cepheids and RR Lyrae stars form the backbone of the cosmic distance ladder, a series of tools that allow us to measure distances from the solar system all the way to the edge of the observable universe. Without these variable stars, we would not know the age of the universe, the rate of its expansion, or the true scale of the galaxies that fill it. Long-period variables, like the star Lyrae we discussed earlier, are another fascinating group of intrinsic variables. These are old red giant stars, near the end of their lives, that pulsate over hundreds of days. Their outer layers expand and cool, then contract and heat up, creating dramatic changes in brightness. Some can fade from naked eye visibility to invisibility, then return to shine brightly again. These stars are crucial for studying stellar evolution, as they show us the final stages of a star's life, before it sheds its outer layers and becomes a white dwarf. Observing long-period variables also teaches us about the chemical enrichment of the universe. As these stars pulsate, They eject heavy elements, like carbon and oxygen, into space elements that later form new stars, planets, and even the building blocks of life. Every time you look at a long-period variable star, you are watching a star create the stuff of the cosmos. The second major category of variable stars is extrinsic variables, whose brightness changes not from within, but from outside forces. The most common type is the eclipsing binary star, a system where two stars orbit each other, and one star periodically passes in front of the other, blocking its light. The most famous eclipsing binary is Algol, the demon star, in the constellation Perseus. Ancient astronomers named it Algol because its regular dimming seemed like an evil omen, but we now know it is a pair of stars, a bright, hot primary star, and a dimmer, cooler companion star. Every 2.87 days, the dimmer star passes in front of the bright one, causing Algol's brightness to drop by nearly 3/4 for a few hours. Eclipsing binaries are not just cosmic curiosities. They allow astronomers to measure the mass size and density of stars with extreme accuracy. By studying the timing of their eclipses, we can calculate the orbital parameters of the binary system, giving us precise data that no other type of star can provide. For decades, astronomers studied variable stars from the ground, but the advent of space telescopes has revolutionized our understanding of these cosmic pulsars. The Hubble Space Telescope has observed Cepheid variables in galaxies millions of light years away, refining our measurements of the Hubble constant, the rate at which the universe is expanding. Today, the James Webb Space Telescope, JWST, is taking this research even further, peering through dust clouds to study variable stars in the earliest galaxies, formed just a few hundred million years after the Big Bang. JWST's infrared vision can detect the faint pulses of variable stars that were invisible to previous telescopes, allowing us to measure the distances to the farthest galaxies ever observed and test our models of stellar evolution in the early universe. These observations are not just updating our numbers. They are challenging our most basic ideas about how stars form, evolve, and die in the harsh conditions of the young cosmos. What makes variable stars so special is not just their scientific value, but their place in the human story of exploration. They are a reminder that the universe is not static, but a living, breathing, ever-changing system. Every pulse of a Cepheid variable, every eclipse of an eclipsing binary, every slow fade of a long-period red giant is a message from the cosmos, telling us about the laws of physics that govern all matter and energy. These stars are humble in appearance, just tiny flickers in the night sky, but they are giants in their importance, holding the keys to the universe's most profound questions. How old is the universe? How big is it? How do stars live and die? How did galaxies form? Every answer leads back to the variable stars that blink and pulse across the cosmos. As we continue to explore the universe, variable stars will remain at the forefront of astronomical research. New surveys, like the European Space Agency's Gaia mission, are cataloging billions of stars in the Milky Way, discovering millions of new variable stars, and refining our measurements of their periods and luminosities. With each new discovery, we get closer to unlocking the full story of stellar evolution and the structure of the cosmos. These stars are more than just objects in the sky. They are teachers, guides, and tools that connect us to the vast, incredible universe we call home. They remind us that even the smallest, most subtle changes in the night sky can hold the greatest secrets, and that the universe is full of wonders waiting to be revealed by those who take the time to look, listen, and learn. Please like, comment, share, and subscribe to the channel.